to look at the video, I had done over there applications of coupled system differential equations. If you recall, there were two examples that were done. One was two beads on a light wire that were vibrating, okay? And we got the natural frequencies and also the mode shapes. And that's prelude to when you'll be taking courses in vibration. You'll be doing multi-degree freedom systems with maybe not just 2 degrees of freedom, but maybe 3, 4, 5. And then the second part of the vibration course, as I mentioned, usually deals with continuous systems, like a vibrating string with mass or a plate, okay? And then the second problem I did remember was a pendulum, 2 simple pendulums, but connected by a spring, okay? So today we're going to look at nonlinear equations, okay? And as I said, most real models of physical systems are nonlinear. Before we go and see how to solve these, and we're just going to solve a very simple class of them, let me give you some examples of where nonlinear equations come up all the time. Okay? In dynamics, you've probably done motion of a rigid body. Here's some arbitrary rigid body R over here in space, right? And it has 6 degrees of freedom, right? Relative to a frame of reference over an inertial frame, say X, Y, Z. For example, this could be a satellite in orbit. Okay, I just draw some blob over there because I don't say that the shape has to be a rod or anything like that. It could just be an arbitrary configuration of bodies. There's 3 translational degrees of freedom, right? You want to track where the satellite is relative to the observing point. You need X, Y, Z, and of course, of what point? Usually go to the center of mass if it's a rigid body, right? So you have this vector R over here that would go to the mass center. That would tell you half the information about the body, right? Basically, where is it located, kind of, in a translational sense. There's also rotation. This thing may have antennas on it, okay, that have to point to certain points on ground stations, right? So it's not enough just to know where it is, or its mass center is, but you also have to know its orientation relative to that frame. So usually what people do is they'll take what's called a body fixed frame over here. I'll put a little one over here. I'll call this maybe X prime, Y prime, Z prime, okay? Not to be confused with X, Y, Z. And that's a body fixed frame. So therefore, as the body translates and rotates, that frame just follows the body motion, okay? So if we knew the orientation of that body frame, which is rigidly attached to the body R, if we knew the orientation of that relative to X, Y, Z, we'd also have the orientation of the body. And that's done in several different ways, things called Euler angles or quaternions. You'll get to that when you take dynamics. But the important thing over there is you have to track 6 degrees of freedom over there, okay? I can write down the translational equations of that. Those will be nonlinear, right? It's just Newton's law, right? I'd say basically for the translational part, I have the total external force is equal to the mass times the acceleration, second of R with respect to time. Okay? It's very important. People, don't say these things fully. Okay, Newton's law for a particle, ever says F equals ma. Suppose I have a rigid body like that. Okay, what's the statement of Newton's law of translation? It says that F, which is the net external force acting on the body, is the product of the mass times the acceleration of the mass center, not the acceleration of this point, okay? Newton's law for a system of particles of a rigid body says F equals ma, where A is the acceleration of the center of mass. And that's basically an equation you have to integrate to find the components X, Y, Z of R, right? But what's the force, basically? It's a very complicated function, right? The force, basically, could be a function of the following. It could be a function of time, right? There's thrusters on the spacecraft. It also could be a function of position, R itself, right? Gravity gradient torque, solar radiation pressure. Also, in an atmosphere, there's drag, so it's a function also of the velocity. And it's a very nonlinear function, okay? So even though it looks simple like this, when you expand this out and you look at X double dot, Y double dot, Z double dot, you get very complicated nonlinear equations, okay? Even for the translation. And for the rotation, this is something that you've probably seen. We have Euler's equation of rotation. Okay, what happens is that there's a well-known result in rigid body dynamics that if you have a rigid body and you go to the center of mass, you can find what's known as principal axes of inertia. Usually the inertia, so-called the inertia tensor, is a 3x3 array. It's symmetric, but it has off-diagonal elements, okay? But you can always find a set of what's called principal axes in the body. You'll do this also when you do mechanics of materials. there'll be so-called principal axes where the inertia matrix is diagonal. And then the equations of motion are the famous Euler's equation. I'll just write them down. We're not going to solve them, just give you an idea. You have I1 omega 1 dot. Remember, that means that's a shorthand notation for the derivative of omega 1 with respect to time, plus, what do you have over here? You've got I3 minus I2, omega 2, omega 3, equals tau 1. I'll tell you what these symbols are in a second, okay? I2 omega 2 dot plus the inertia difference I1 minus I3, in this case, omega 3 omega 1 is equal to tau 2. Finally, the third equation, this is 3 degrees of freedom, right? I3 omega 3 dot plus I2 minus I1 omega 1 omega 2 equals tau 3. Okay, what are all these symbols? Omega is a vector, has components omega 1, omega 2, omega 3. Those are the components of the angular velocity of this body in the body frame. Okay? I1, I2, I3 are the principal moments of inertia. Basically, what they tell you is how the mass is distributed, what a moment of inertia is, right? Clearly, the rotational dynamics depends upon how the mass is distributed. You know, is there a heavy payload over here? Is there some antenna over here, right? That'll change the inertia matrix, okay? But the numbers, I1, I2, or 3 are constant, at least for a rigid body, okay? We've got the i's and the omegas, okay? And tau 1, tau 2, tau 3 are the components of the net external torque acting on the spacecraft about the center of mass. Right? Just like from the forces, we had aerodynamic drag, right? There's a force with the aerodynamic drag acts over here. It puts a torque about the center of mass. Solar radiation pressure, right? Thrusters on the spacecraft. And that's used to control it, right? If you have this spacecraft and this guy has to point to a ground antenna, you have to fire a thruster so that, or rotate a gyroscope so the thing reorients itself, okay? So it's called active control of the spacecraft. But from the mathematical point of view, what I want you to understand is that you have to solve these guys for omega 1, omega 2, and omega 3 as functions of time. Given the initial conditions, of course, omega 1, omega 2, omega 3 times 0, given these guys, and you can see, even if these torques were simple, see how it's nonlinear, omega 2, omega 3? It's the product of the dependent variables. When you have the product of dependent variables, it's always nonlinear, okay? So even something like a rigid body, and believe me, when you do spacecraft, you don't model as rigid body, you have to model as a flexible body, because that's solar rays and all types of stuff. But even the simplest concept of a single rigid body in space, when you look at the equations of motion, they are very difficult to solve analytically, okay? So that's an example, another example of a nonlinear equation. Let me just give you another one. I'll try to draw this as best as I can. Let's just do a particle in the xy plane, okay? And it's going in some type of path like this, okay? I'll just draw a little tangent over here. Yeah, so that's supposed to be a straight line, but I want to go to the origin, so I'm going to have to just redraw my axes. So here's my xy, here's my origin, here's my xy plane, okay? This makes a certain angle of theta, let's say with the horizontal, right? And suppose I have just a particle, okay? I take this, this particle going in the xy plane, and I want to know its equations of motion. Suppose it's in a gravity field, so we have mg acting down, right? That's if it's near the surface of the Earth, at least, mg. Okay, and let's put some air resistance on. So we're going to have a resistive force. And remember, air resistance is what? It's a drag. It always opposes the motion. So if I'm going to the right, it goes to the left. Here, I draw the tangent to that point, and therefore the aerodynamic drag, we'll call it R, goes to the left and it's tangent at that point. Okay. So, suppose I want to write the equations of motion for this system. Okay? I'll use Newton's law, okay? So I have the mass times the acceleration, right? R is just the position vector from O to there, xi plus yj, right? That equals the net external force on the thing. What about gravity, which is minus mg, right? And now I have to be careful, I also have resistance, right? So I got minus the resistive force, right? Times a unit vector along that direction, which is dx dsi plus dy dsj, where s is the arc length. You recall from calculus, so maybe you'll look it up, that the unit tangent vector to a curve, if x and y are the coordinates on the curve and s is the arc length, the tangent vector is dx ds dy ds. Okay? And you see when I have the minus r over here, because dx ds dy ds is a unit tangent vector going along the direction of motion, increasing arc length, but the resistance opposes that, that's why the minus is there. Okay, let's put this in component form and see what we get. We get m times the second derivative of x with respect to time, right? Well, that should be minus mgj, right? Because it's a vector. So now I only have minus the resistance times dx ds, right? And the other equation of motion, m times the second derivative of y with respect to time, is minus the resistance dy ds, right? And then we also get a minus mg on there. Okay? Now, what I want to do is get equations where the independent variable is time and the dependent variables are just x and y, right? I want to get rid of that arc length. Well, that's easy enough by the chain rule, right? dx ds is just dx dt over dy dt. dx ds, yeah. Sorry, dx ds, let's divide through by dt. It becomes dx dt, which is the x component of velocity. I'll just say it's x dot divided by the speed. Remember that ds dt is the speed of the particle, okay? And similarly, I need a dy ds over there. dy ds, divide top and bottom by dt, you get y velocity divided by the speed. So when we put this all together, we find for the x equation of motion, we'll have the following. The second derivative of x with respect to time is equal to minus resistive force divided by the mass, dx ds, which is basically dx dt divided by the speed. Okay? And for the y equation of motion, we have the second derivative of y with respect to time is equal to minus little g. Okay, that's what we expect, right? And minus r over m, resistive force divided by the mass. And then we have this dy ds, which we just showed was dy dt divided by the speed. Okay. Now, let me show you why it's nonlinear. What's v, the speed? That's the square root of x dot squared plus y dot squared, right? You have dx dti and dy dtj, that's the speed. So in both of these equations, we have in the denominator the square root of dx dt squared plus dy dt squared. So it's coupled, right? X double dot, and because of the speed over here, we get not only x dot in there, but also a y dot in there. Similarly, in equation on y double dot, here, you got a dy dt, but unfortunately divided by the speed, that brings x into the equation. Square x dot squared plus y dot squared. Even making it more complicated is the resistance. I just put a symbol there, R. But what really is R? R basically is a complicated function of y and the speed. Why is that? Let's say it's aerodynamic drag. Okay, we all know that the atmosphere, the density changes as a function of altitude. So therefore, the density, the resistive force depends upon y, which would be the distance above the ground, right? It's also a function of the speed, right? For slow motion, it's proportional to v. For higher speeds, it goes as v squared, and it gets much more complicated when you go to hypersonic speeds, okay? So it's a mess, yeah.
You also have to take into account temperature, humidity.
Yeah.
All that good stuff.
Yeah, exactly. Yeah, I mean, and these are never, it really can't be done analytically. You have, like I said, you have a lookup table about where you are and the temperature, and that will dictate what the density is. Rho is a function of altitude. Okay. All this is just to show you basically that nonlinear equations are not uncommon in engineering practice, and something has to be dealt with. Okay. Now, like anything, if there are certain classes that can be solved analytically, we should look at them, okay? To say basically that, anything getting practice is going to be just intractable analytically, and we'll go to the computer, is okay. But even when you go to the computer, okay, it's always good to have certain reference cases to check. And I always do this. If I'm using a new computer program, a code that I never used before, the first thing I do is I make up a problem. Of course, it's applicable to the code, but also one where I know what the answer is. Not that I don't trust the code, I don't trust myself. Maybe I'm not using it correctly, whatever. And therefore, you have at least some confidence that you're using the code correctly because you know a priori what the answer is. Okay, then just checking at the code, gives you that. And then, of course, when you get something that's intractable analytically, you have no choice but to do some numerical stuff on it. Okay. But there are plenty of problems which we're going to actually do later. I don't know how much time we're at the end of the term, but I'm going to try to do as many as I can that illustrate these analytical techniques, and they're not uncommon problems, and it's good to know how to do them. Okay? So, I showed you systems of nonlinear simultaneous differential equations. We're going to start off real simple. We're going back again, in our case, to just one independent variable, and again, because it's a math book, we won't call it t, we'll call it x, and we'll call the dependent variable y. So we just look at a single equation, not a system, but a nonlinear differential equation, okay, where, so this topic would be nonlinear, second order. Ordinary differential equations, ODE. Okay, now I can be really cryptic and I can say, well, what is it? It's some function of x, y, y prime, y double prime is equal to 0. That's the most general nonlinear second order equation, right? Where y prime, of course, indicates dy dx and y double prime is sec y respect to x. There's no way to solve that for arbitrary f. Okay, we have to look at special cases. And the cases, there are two cases that come up in practice that many times you can actually get a solution. We'll talk about them, then we'll illustrate them on some problems. Okay, the first one, case 1, is dependent variable is absent. Dependent variable absent. By that, what I mean, it doesn't appear explicitly, okay? So the equation now is f of x, y prime, y double prime is equal to 0. Of course, y is still in there because through y prime, y double prime. What we mean when the dependent variable is absent is that if you kind of just regard x, y, y prime, y double prime as independent variables,